All right, so let's go ahead and start going through the practice final here. Question number 1, a survey asked 33,193 homeowners how many pets they owned. And the results were as follows. All right, so we've got this table here. It says, what is the probability that a sampled homeowner has more than one pet? It's pretty straightforward, right? Basically, more than one, we would take the number of homeowners corresponding to 2, 3, 4, or more. We would add up those numbers and divide by the total, right? So let me go over to a whiteboard here. This is problem 1. And we've got probability of more than one pet. From the table, we've got 8831 who had 2 pets, 6265 who had 3 pets, 551 who had 4 or more. And that's divided by the total of 33193. You work that out, you would get 0.471. Okay. That's question number 1. 0.471. So it looks like the answer would be A. Okay. All right. Number 2, a section of an exam contains 2 multiple choice questions, each with 3 answer choices listed A, B, and C. Assuming the outcomes to be equally likely, find the probability as a reduced fraction that at least one answer is A. And the hint here is to list all the outcomes of the sample space first. All right. So what I did, the tool I used to help with the sample space part is a tree diagram, where I basically said, okay, we've got one question with 3 answer choices, right? Those answer choices are A, B, C. And then regardless of which choice you choose on the first question, the second question also has 3 answer choices. So I've got, if I choose A for the first question, then I can choose A, B, or C on the second, right? Or if I choose B on the first question, I could choose A, B, or C on the second. Or if I choose C on the first question, I could choose A, B, or C on the second. So if I trace through all my branches and write them down, I would get the sample space. So if A is chosen first, then I could choose A second, or B second, or C second. If B is chosen first, then I could choose A second, or B second, or C second. And if C is chosen first, I could choose A second, B second, or C second. And the question was to find the probability of at least one A, right? So at least means 1 or more. So I'm going to circle, this is my sample space, right? There's 9 outcomes. I'm going to circle the outcomes that that have at least 1 A. This one does. This one does. This one does. This one does. And this one does, right? Any outcome that has an A in it, or 2 A's in it, would count, right? The ones that are not in the event are the ones that don't have any A's in them. So I have 1, 2, 3, 4, 5 outcomes that have at least 1 A. So we've got at least 1 A, 5 outcomes that have at least 1 A, and there are 9 outcomes total. And that fraction is already reduced. So that's the answer. Okay. Or C. All right. Moving on to 3. On a certain day, a cheese packaging facility packaged 510 units of mozzarella cheese. Some of these packages had major flaws, some had minor flaws, and some had both major and minor flaws. So the table presents the results. It says find the probability that a randomly chosen cheese package has a flaw, either major or minor. So I'm basically finding a probability of a compound event using an OR. So here's what that would look like. I'll squeeze it in over here. Basically got probability of major or minor. So the general addition formula says this is equal to the probability of major plus the probability of minor minus the probability of both major and minor. Okay. All of these can be taken from the table, right? So like, for example, the probability of a major flaw, I would go to the row labeled major flaw, and I would add up the numbers in that row. 25 plus 36, those add up to 61, and I would divide that by the total, which is 510. Okay. So that looks like 61 over 510. Probability of a minor flaw, I would find the column that's labeled minor, and I would add up the numbers in that column, and they add up to 92, and divide that by 510. And then major and minor, I would find where the row labeled major intersects with the column labeled minor. And you would see the number 25 there, and that is out of 510. So that works out to be 128 over 510, or 0.251 as the answer. Okay. So yeah, the answer is A. All right. Let's move on to number 4 here. A geneticist is studying 2 genes. Each gene can be either dominant or recessive. A sample of 100 individuals is categorized as follows. Right, so we've got the rows gene 1 dominant, gene 1 recessive, and then gene 2 dominant, gene 2 recessive. Given that gene 1 is dominant, what is the probability that gene 2 is dominant? So this is a conditional probability. Okay. Clear this. So here's how I have this set up. This is number 4. I've defined event A as the event that gene 1 is dominant. I have defined event B as the event that gene 2 is dominant. Okay. And so what I'm trying to find is the probability of B given A. The probability that gene 2 is dominant given that gene 1 is dominant. Okay. This is equal to the probability of A and B divided by the probability of A. Okay. A and B, this is the probability that both genes are dominant, right? And to find that probability, I would go to my table and I would find where the gene 1 dominant row intersects with the gene 2 dominant column. And I see that's a 9, and I divide that by the total, which is 100, right? So the probability on the top is 9 over 100. So this is equal to 9 over 100. P of A is the probability that gene 1 is dominant. And for this one, I find the row labeled gene 1 dominant, and I add up the numbers in that row. 9 plus 6 is 15, and divide that by 100. Okay. So on the bottom, I have 15 out of 100. I'm dividing two fractions that have the same denominator, so that's going to simplify down into just 9 divided by 15, or in decimal form, 0.60. Okay. So that is how that one's done. Right. Back over here. That's number 4. So the answer is C. Okay, let's move on to number 5 here. The number of customers in a line at a supermarket express checkout counter is a random variable with the following probability distribution, and we're asked to compute the mean of the distribution. So to find the mean of a probability distribution for a discrete random variable, you take each x value and multiply it by its corresponding probability, and we add up the products. Okay. So it's going to look like, so the formula is just this sigma x times p of x. And it looks like this: 0 times 0.08 plus 1 times 0.23 plus 2 times 0.33 plus 3 times 0.21 plus 4 times 0.08 plus 5 times 0.07. Okay. That equals 0 plus 0.23 plus 0.66 plus 0.63 plus 0.32 plus 0.35, and those add up to equal 2.19. Okay. And going forward for the rest of the problems, I'll also just kind of make a note about if you the proper function to use if you want to use your TI-84. With this one, you would want to use 1-varstats. And what you would do is you would enter in your list editor, you would enter the x values into L1, and then the p of x values into L2. Then you would run this command. And for list, you would put L1, and frequency list, you'd put L2, and then you just run it, and it would give you the mean. So. All right. Number 6. A student takes a true-false test that has 7 questions and guesses randomly at each answer. Let X be the number of questions answered correctly. Find the probability that 5 correct answers. So this is a binomial probability problem, right? Because we have 7 trials, 7 questions. Each trial has 2 possible outcomes, true, false, right? And if we're just guessing randomly, the probability of success for each trial is the same. It would be just 0.5. And the trials are independent, right? So it meets all those requirements. So what I'm going to do is I'm going to go through how to find this using the binomial probability formula. Switch over there. I'm going to need a bit more room, so I'm going to clear this. So this is 6. The formula is P of X equals n factorial divided by x factorial and minus x factorial. P raised to the power of x times 1 minus p raised to the power of n minus x. Okay. So what we have, n is the number of trials, which in this problem was 7. X is the number of successes. We define success as getting the correct answer. We want to find the probability of 5 successes. P is the probability of success on a single trial. If you're guessing randomly, it's true, false. Your probability of success is 0.5 or 1/2. So first of all, I'm going to just take this portion of the formula that has the factorials, which is really the combinations formula, and work that out. So if I just have n factorial divided by x factorial n minus x factorial, this is equal to 7 factorial divided by 5 factorial, and 7 minus 5 is 2 factorial. This is equal to 7 times 6. I'm going to just simplify this down part of the way, like this. Divided by 5 factorial. 2 factorial is 2 times 1. So now I can cancel the 5 factorial here with the 5 factorial here. This just ends up being 7 times 6 over 2, which equals 21. Okay. So coming over here, probability of 5 successes. This factorial piece is just 21, and that gets multiplied by 0.5 raised to the power of x, which is 5, times 1 minus 0.5, which is also 0.5, raised to the power of 7 minus 5, which is 2. You can easily plug that into your calculator and you get 0.164. Okay. That's one way to get the answer. Another way, if you want to use your calculator, you could use the binom PDF command. Okay. And it's pretty straightforward. You just enter in your n value, your x value, your p value, and it will give you the result there as well. So. All right, now we start getting into some problems related to the normal distribution. So for 7, find the area under the standard normal curve that lies between z equals negative 2.1 and z equals 0.6. Okay, so I'm going to start by just sketching that curve. So we're down here. Okay, So I've got standard normal curve, which is centered over 0, right? Negative 2.1 is down here somewhere. 0.6 is up here somewhere. And we're trying to find the area in between. So to find the area in between these, I'm going to use the table. So I'll start, let's see here. What I'm basically going to do is I'm going to find the area to the left of 0.6. And then I will subtract from that the area to the left of negative 2.1, right? So I'll find the area to the left of both z-scores, and I'll subtract the smaller area from the larger one, and that will give me the area in between. So let me bring up the table here, which is right here. So the area to the left of 0.6 would be points. I find 0.6, and then I find the number under 0.00, and it says 0.7257. And then I subtract from that the area to the left of negative 2.1, and that's up here. Okay, it's right here, 0.0179. Okay, so I have 0.7257 minus 0.0179. Let's go back to my whiteboard. That's from the table. 0.7257 minus 0.0179. And this equals 0.7078. Alternately, if you want to use your calculator, you could use the normal CDF command. And that would give you the area. Keep in mind that the answer given by the calculator might differ just slightly from the answer given by the table because of rounding, but they should be pretty close. In either way, when you're selecting your answer choice, it should be close enough to the point where it would be obvious what the correct answer is. In this case, you would want to choose D. Okay, it's that one. Yeah. Okay, coming down to number 8. A bottler of drinking water fills plastic bottles with a mean volume of 999 milliliters and a standard deviation of 7 milliliters. The fill volumes are normally distributed. What proportion of bottles have volumes between 993 milliliters and 996 milliliters? So I'm going to start by sketching a normal curve representing this. Then we'll have to convert, in order to use the table, I will have to convert both 993 and 996 into z-scores. And then I can proceed in the way I did in problem 7 to find the area in between those z-scores. Okay. So here is what that looks like. Yeah, I'm going to need more room, so. Up to number 8. Here's my normal curve. It's centered over 999. I'm trying to find the area in between 993 and 996. And I've got sigma equals 7. That's my standard deviation that was given. Trying to find the area in between here. Okay. So in order to use the table, I have to convert this into the standard normal curve. And I do that using the z-score formula, which looks like x minus mu over sigma. So I'll convert both 993 and 996 into z-scores. I'll start with 993. I'm just going to do a z with a subscript of 993. this looks like the X value is 993. The mean is 999. Standard deviation is 7. So round this to 2 decimal places. So I get negative 0.86. And then do it again for 996. So 996. And this looks like 996 minus 999 divided by 7. That equals negative 0.43. And so once again, to find the area, I'll use the table to find the area to the left of both z-scores and subtract the smaller one from the larger one. So that looks like the area to the left of negative 0.43, 0, 1, 2, 3 is going to be right here, okay? Because it's negative 0.4 and then it's underneath 0.03, right? And then the area to the left of negative 0.86, that will be right 0.8, 0, 1, 2, 3, 4, 6. That'll be right here, 0.1949, right? Because it's negative 0.8 and the 6 is up there, okay? So it's going to be 0.3336 minus 0.1949, okay, to get the area in between. So I've got 0.3336 minus 0.1949, and that equals 0.1387. So yeah, that's the answer. Or if you use the calculator, once again, you could use normal CDF. And that would also give you the answer. Okay. Okay, go back to my exam here. Number 9. These next to you are sampling distribution problems. A sample of size 41 will be drawn from a population with a mean of 16 and a standard deviation of 10. Find the probability that the sample mean will be greater than 18, right? So we're asking for the probability of a sample mean. The sample mean is the random variable in this case, so we'll use the sampling distribution. And remember that the central limit theorem says that if your sample size is greater than 30, then the sample mean will be a random variable that is normally distributed. And the standard deviation will be the population standard deviation divided by the square root of the sample size. So this is number 9. Central limit theorem says that the mean of the sampling distribution will be equal to the population mean, which in this case is equal to 16. Standard deviation of the sampling distribution will be population standard deviation over the square root of n, or 10 over the square root of 41. And because the sample size is greater than 30, this will be a normal distribution. So this represents the distribution of all sample means based off of samples of size 41. This is centered over 16. And I'm trying to find the area under this curve that's to the right of 18, because it said, you know, what's the probability that the sample mean is greater than 18? Because this is a sampling distribution, I'll use this slightly modified version of the z-score formula, which looks like x bar minus mu over sigma over the square root of n. Okay, and my sample mean is 18. My population mean is 16, and I divide by 10 over the square root of 41, and that equals 1.28. And then I'll go to my table, and the table will give me the area to the left of 1.28, and I'll take 1 minus that to get the area to the right. Okay. So I have 1.2 and come over here till I'm underneath 0.08. I get 0.8997, and I'll take 1 minus that. So 1 minus 0.8997. So whoopsies, sorry, ignore that. 1 minus 0.8997. That equals 0.1003 as my answer. Or alternately, if you choose to use the calculator, again, it would be normal CDF. Just your general function for finding an area under a normal curve. Okay. All right. Just did 9. We're up to 10, right? At a cell phone assembly plant, 76% of the cell phone keypads pass inspection. A random sample of 91 keypads is analyzed. Find the probability that more than 75% of the sample keypads pass inspection. All right, so this is again a sampling distribution problem, but we will use the central limit theorem for a proportion to do this. Okay. The population proportion is the 76%, right? And we're trying to find the probability that the sample proportion is greater than 75% or 0.75. Okay. So the central limit theorem for a proportion says this. It says that the mean of the sampling distribution is equal to the population proportion, which is equal to 0.76. Standard deviation of the sampling distribution is equal to the square root of p times 1 minus p over n, equal to the square root of 0.76 times 1 minus 0.76 over sample size was 91. So this is equal to about 0.04477. And I'll treat this as a normal distribution. And the mean is 0.76. Probability said, what's the probability that more than 75% pass inspection? So that's the probability that the sample proportion is greater than 0.75. So that's the area that we're trying to find. The z-score formula I will use looks like this. P hat minus p over the square root of p times 1 minus p over n. This equals 0.75 minus 0.76 over, I calculated the standard deviation right there, 0.04477 or negative 0.22, okay? And if I go over to my table, I would find the area to the left of negative 0.22, which is 0.4129 right here. And I'll take 1 minus that because I want the area to the right, okay? 1 minus 0.4129. One minus 0.4129 equals 0.5871, or again, if you want to use your calculator, normal CDF is what you'd want to use for that. Okay. So now we're going to start going over some problems that deal with confidence intervals. So we're down to number 11 here. A random sample of 110 adults is chosen, and their mean serum cholesterol level is found to be 203 milligrams per deciliter. assuming that the population standard deviation is sigma equals 42, compute a 95% confidence interval for the mean serum cholesterol level for adults. Okay, so sigma is given, and we are trying to estimate the value of a mean. So the formula that we want to use for that is, let's write it down here. X bar minus Z alpha over 2 times sigma over the square root of n is less than mu is less than X bar plus Z alpha over 2 sigma over the square root of n. Okay. So let's write down what we're given. The sample size is given. That was 110. The sample mean is given in the problem as 203. Sigma is given, and that is 42. Z alpha over 2 is the critical value, which is not directly given, but I can look it up. And we were asked for a 95% confidence interval. So the place I find this is I will go to the student's t distribution table, and I'll go to the very bottom row, and I'll choose the z value corresponding to 95%, which is 1.96. So that's my critical value there. This is equal to 1.96. Okay, so now I'll calculate the margin of error. The margin of error is z alpha over 2 times sigma over the square root of n, and this equals 1.96 times 42 over the square root of 110. And I'll just round this to a whole number. That's equal to 8. And so now I have sample mean minus 8, sample mean plus 8, and that ends up being 195 up to 211. Okay. If you want to use the calculator, the function you would use is z interval. And it's pretty, yeah, that's where you'd go. All right. So 12. In a sample of 26 children, the mean age at which they first began to combine words was 16.54 months. With a standard deviation of 5.32 months, it is reasonable to assume that the population is approximately normal. Construct a 90% confidence interval for the mean age at which children first begin to combine words. Okay, once again, we're estimating a mean, but this time sigma, the population standard deviation, is not given. We are given a sample standard deviation. So we'll use, let me write down the formula here. It's the formula that involves the t values for the critical values. So it looks pretty similar to this formula, except sigma gets replaced with s and z gets replaced with t, okay? I'll write that down. Okay, so I've got all right, so now as far as what's given, sample size is given, n is equal to 26. Sample mean is given in the problem, it is equal to 16.54. And sample standard deviation is given, it is 5.32. And then to find the critical value, I'll use the student's t distribution chart. I'll need the degrees of freedom for that. And the degrees of freedom is one less than the sample size, which is 25. And let's see, go back over here. We're also told that the level of confidence we want is 90%. So I come over here, I find 25 degrees of freedom. I move across this row, I find 90%, 25, where those meet, I get 1.708. So that is my critical value right there. Okay, 1.708. Okay, so T alpha over 2 equals 1.708. So the margin of error is going to be the t-value, 1.708 times s, which is 5.32 over the square root of n, square root of 26. And that equals about 1.8. And we subtract and add that from the sample mean. So I got 16.54 minus 1.8 and 16.54 plus 1.8. So my interval is 14.8 comma 18.3. Okay. Or you could use the calculator, and the function you'd want here is t interval. Okay. That is that. Number 13, this is confidence interval for a proportion. In a survey of 299 registered voters, 130 of them wished to see Mayor Wafflesgate lose her next election. Construct a 99% confidence interval for the proportion of registered voters who want to see Mayor Wafflesgate defeated. Okay. So the formula for this one is the confidence interval for a proportion formula. So it looks like p hat minus z alpha over 2 square root of p hat times 1 minus p hat over n less than p hat plus z alpha over 2 square root of p hat 1 minus p hat over n. Okay. So what's given? The sample size is given 299. My x value is given as 130. So that means p hat is equal to x over n, or 130 over 299, which equals 0.435. Okay. Z alpha 2, alpha, the critical value, the z value, I have to look that up. Okay. Says we want 99% confidence. So I'll go over to students T and we'll come down to the very bottom row. For 99%, the z value is 2.576. So that's my critical value. .576. Okay. So the margin of error is 2.576 times the square root of 0.435 times 1 minus 0.435 over n, which is 299. That works out to be about 0.074. And I subtract that and add it. Okay. So my confidence interval is about 0.361 up to 0.509. Or if you want to use the calculator, you would use 1-prop z int for that. Okay. Okay. So now we're moving on and we're doing a few questions related to hypothesis testing, which was the last topic we covered in the class. This first one is just going over basically, understanding how to conclude a test, right? So it says, a grocery store owner claims that the mean amount spent per checkout is more than $77. A test is made. The null hypothesis, which says that mu is equal to $77, and the alternate hypothesis says that the mean is greater than $77. The null hypothesis is rejected. State the appropriate conclusion. So if the null hypothesis is rejected, that means the alternate hypothesis is accepted. The alternate hypothesis says that the mean checkout amount is greater than $77. So you would just choose C as your answer. And that's it. Okay. All right. For 15, mercury is a heavy metal that can cause severe health problems in even small concentrations. Fish and shellfish efficiently concentrate mercury into their flesh. So it is important to monitor seafood for its mercury content. An extensive study conducted in 1980 concluded that the mean mercury level in oysters from the White Bear Estuary was 0.02 parts per million, with a standard deviation sigma of 0.02 parts per million. In 2012, a sample of 48 oysters from the same estuary exhibited a mean mercury concentration of 0.005 parts per million. Can you conclude that the 2012 mercury concentration is lower than in 1980? Use the 0.01 level of significance. So we need to establish our hypotheses, find a test statistic and a p-value, and then conclude the test. And we're doing a test about a mean, and sigma is known. And it looks like it's going to be a left tail test because it says lower right there. Okay. So I'm going to flip over here. Yeah. This is 15. The null hypothesis is the assumption that nothing has changed, and that would be the assumption that the mean is equal to what it was, I think, in 1980, which was 0.02. The alternate hypothesis is the assumption that it's now lower, and that would be that the mean is less than 0.02. And we're testing at the 0.01 level of significance. So I have to find the next step is to find the test statistic, which is a z-value, because sigma is given. So it's x bar minus mu over sigma over the square root of n. And that's equal to 0.005 because the sample mean is given as 0.005 minus 0.02. Remember, when we calculate the test statistic, we are assuming that the null hypothesis is true. So that's why I plug in 0.02 for mu. Sigma is given as also 0.02. Just a coincidence that those are the same value. And that's divided by the square root of 48. This is actually a really small z-value. It turns out to be negative 5.2. So the p-value would be the area under the standard normal curve chart. That's to the left of negative 5.2. Okay. Let's see if we can find it on the chart. So the chart actually only goes down to negative 3.79, right? So, so the smallest area on the chart is 0.0001. My Z value is negative 5.2, right? So basically all I can conclude is that my p-value is smaller than 0.0001, right? It's a very small p-value. So from the chart, my p-value is less than 0.0001. Alpha is 0.01, right? So clearly my p-value is smaller than alpha. Is less than alpha. So that means I will reject the null hypothesis. Okay. And that tells me, if I'm rejecting, that I would answer A, right? Yes, the mercury concentration appears to be lower in 2012. The alternate hypothesis appears to be true. Okay. All right. Let's come down to 16. A market research firm reported that the mean annual earnings of all family practitioners in the United States was $180,439. A random sample of 37 family practitioners in New York that month had mean earnings of a sample mean of $197,478 with a standard deviation of 35,551. You wish to test whether family practitioners in New York make more than the national average. State a conclusion regarding the null hypothesis. Use the 0.05 level of significance. Okay. So let's come over here. The null hypothesis is the assumption that nothing has changed, and that is that mu is equal to 180,439, what it was before. The alternate hypothesis is the assumption that it's now increased, so mu is now greater than 180,439. So it's a right tail test. We're testing at the 0.05 level of significance. In this one, sigma is not given. We're only given the sample standard deviation. So the test statistic will be a t-value, which looks like x bar minus mu over s over the square root of n. Okay. X bar, the sample mean, is given as 197,478. And for mu, we plug in 180,439. S is given as 35551 over the square root of 37. That works out to be 2.92. It's a right tail test, so the p-value will be the area under the student's t distribution curve to the right of 2.92. So I'll use the table to kind of at least narrow that down. So my sample size is 37. My degrees of freedom is 36. So let me come over here to the table. So I've got 36 degrees of freedom, and in this row, I want to find the two values on either side of 2.92. That will be these two values, right? 2.990 and 3.333. Now I'll come up here and I'll look at the two area and right tail values, which are right here, right? So my p-value, it's like my p-value falls between, is that right? 36 degrees of freedom, 2.99. Yeah, I'm looking at 2.9. Oh, sorry. It's actually these two, right? Because my t-value is 2.92. So 2.92 falls between 2.719 and 2.990. So my p-value then falls between 0.0025 and 0.005. Okay, write that down. So my p-value falls between 0.0025 and 0.005. Okay. Clearly, then my p-value is smaller than 0.05, right? My p-value is less than alpha, so I will reject the null hypothesis, right? And I will accept the alternate hypothesis, which is that the mean incomes have increased, right? Let me just make a comment for number 15. The function for the calculator would be z-test, okay? And down here, you would use t-test. And if you want an exact p-value, you would need to use the calculator. If you did use the calculator, you'd get a p-value off the calculator of about 0.0003. Okay, the chart only allows me to narrow it down to within that range. All right, almost done here. 16. Okay, 17, here we're testing a proportion, right? A poll surveyed 511 video gamers, and 148 of them said that they prefer playing games on a console rather than a computer. An executive at a game console company claims that more than 25% of gamers prefer consoles. Does the poll provide convincing evidence that the claim is true? Use the 0.01 level of significance, right? It says more than 25%, so that suggests a right tail test, okay? So this is 17. My null hypothesis will be the assumption that P is equal to 25% or 0.25. My alternate hypothesis will be the assumption that P is greater than 25%. Okay. I'm testing at the 0.01 level of significance. I'm going to need my sample proportion. This is from the data in the problem. This is equal to 148 over 511, which equals 0.29. Clearly, my sample size here is 511. My test statistic will be a z-value given by p hat minus p over the square root of p times 1 minus p over n. P hat is 0.29. For p, I plug in 0.25. Right, square root of 0.25, 1 minus 0.25 over 511. And that works out to be 2.07. In the interest of time, I'm not going to flip over to the table, but you'd use the standard normal curve table, and you'd find the area to the right of 2.07, right? So the p-value, it's going to be 1 minus 0.9808. 0.9808 is the area to the left, which you find from the table. And you take 1 minus that to get 0.0192. That is greater than alpha, right? Because my alpha value is 0.01. So I do not reject the null hypothesis. Okay. And for the calculator, you would want to use 1-prop z test for this one. Okay. I'm going kind of quickly, but almost out of time. So does the poll provide convincing evidence that the claim is true? You would answer no. The answer there is B. Okay. All right, so these last three are from the chapter 11 material, right, where we're kind of doing comparisons between populations. 18, the concentration of hexane, a common solvent, was measured in units of micrograms per liter for a simple random sample of 16 specimens of untreated groundwater. taken near a municipal landfill. The sample mean was 561 with a sample standard deviation of 5.9. 15 specimens of treated groundwater had an average hexane concentration of 556.6 with a standard deviation of 5.7. It is reasonable to assume that both samples come from populations that are approximately normal. Can you conclude that the mean hexane concentration is less in treated water than in untreated water? Use the 0.01 level of significance. Okay. All right. See if we can do this here. I'm going to start by just writing down the data that I'm given. So for untreated, what I'm told is that the sample mean, which we'll call X1 bar, is equal to 561. Sample standard deviation is given as 5.9. Sample size is given as 16. For the treated water, the sample mean, which we'll call X2 bar, is given as 556.6. Sample standard deviation is given as 5.7. Sample size is given as 15. My hypotheses, null hypothesis would be the assumption that the mean is the same for both. So mu1 equals mu2. Alternate hypothesis would be the assumption that the concentration is less for the treated. So I've got mu1 and I'm comparing it to mu2. And mu2 represents treated. So I want the direction of that to point like this, right? Because mu2 has to be less than mu1 or mu1 greater than mu2. So it's a right-tailed test. The test statistic, this is from 11.1, is given by X1 bar minus X2 bar minus mu1 minus mu2 over square root of S1 squared over N1 plus S2 squared over N2. Okay. And this is equal to 561 minus 556.6. Okay. For mu1 minus mu2, I'll replace that with 0 because I am assuming the null hypothesis is true, right? So I assume those are equal to each other. This is divided by square root of 5.9 squared divided by 16 plus 5.7 squared divided by 15. And this is equal to 2.112, okay? And then it's a t-value, so you would use the table. The degrees of freedom will be based off of the smaller of the two samples, which is 15, so the degrees of freedom would be 14. And then we did just like what we've done before. You go to the table, you find the row corresponding to 14 degrees of freedom. You find the two numbers in that row that are on either side of 2.112, and then go up and look at the area and right tail values. That will tell you that the p value 0.00025, basically your p value falls somewhere between 0.025 and 0.05. Okay. Alpha, I forgot to write that down, but alpha was given in the problem as 0.01. So it looks like my p-value is greater than alpha. So that means I will not reject the null hypothesis. Okay. And that's how you do it. And then the for the calculator, you could use 2-samp t-test to do that. Okay, and that's it. Okay. So it says, can you conclude that the mean hexane concentration is less in treated water than in untreated water? You would answer no. Because we did not reject the null hypothesis, the answer is no. Okay. Okay, 19, we're comparing two proportions in a random sample of 380 cars driven at low altitudes. 42 of them exceeded a standard of 10 grams of particulate pollution per gallon of fuel consumed. In an independent random sample of 90 cars driven at high altitudes, 24 of them exceeded the standard. Can you conclude that the proportion of high altitude vehicles exceeding the standard is greater than the proportion of low altitude vehicles exceeding the standard at a 0.01 level of significance? Okay. All right. So this is 19. This time we're comparing two proportions, right? Again, I'm just going to write down the data that I'm given. For low, I'm going to say that P1 hat, actually, sorry. Let's try this again. Okay, 19. Okay, so for low, I have a sample size N1 of 380, X1 of 42. And so my P1 hat value is 42 out of 380, or 0.11, okay? For high, I have N2 equals 90, X2 equals 24, and P2 hat equals then 24 out of 90 equals 0.27, okay? I'm also just gonna, for this, I'm gonna need the pooled proportion as well. I'm just gonna calculate this over here. This is where you add up the X values and divide by the sum of the N values, okay? So that's 42 plus 24 divided by 380 plus 90, which is about 0.14. Okay. Null hypothesis. We are assuming that the population proportions are the same. Okay. Alternate hypothesis. We are assuming that we're comparing P1 and P2. We're assuming here that the concentration, let's see. Let me go back and just read the problem real quick. I'm short on time, but can you conclude that the proportion of high altitude vehicles exceeding the standard is greater than the proportion of low altitudes, right? So because P2 represents high altitude and P1 low altitude, then this needs to be a left tail test, right? P2 greater than P1 or P1 less than P2. Okay, the test statistic is given by P1 hat minus P2 hat over square root of P hat times 1 minus P hat times 1 over N1 plus 1 over N2. Okay. And this is equal to 0.11 minus 0.27 divided by square root of 0.14. That's the pooled proportion, right? It's 0.14 times 1 minus 0.14 times 1 over 380 plus 1 over 90. Okay. And that works out to be negative 3.83. It's a left tail test. So the area, the p-value would be the area to the left of negative 3.83 under the standard normal curve. The table can only tell me that my p-value is less than 0.0001. Clearly then my p-value is less than alpha. So I will reject the null hypothesis on this one, okay? Calculator, you would want to use 2-prop z test. That's what you want to use on the calculator. Okay. So I rejected the null hypothesis. It says, can you conclude that the proportion of high altitude vehicles exceeding the standard is greater than the proportion of low altitude vehicles exceeding the standard? The answer is yes, right? Okay, I'm going to go ahead and work out the last one. I know we're basically out of time. If you cannot stay, I'll post the recording and you can watch it later. But if you have time just to stick around, I will go ahead and work out the last one as well. So this is from 11.3, a matched pairs problem. Okay. Following is a sample of 5 matched pairs. Let mu1 and mu2 represent the population means, and let mu d equal mu1 minus mu2. A test will be made of the hypothesis. The null hypothesis is the assumption that mu d equals 0. The alternate hypothesis is the assumption that mu d is greater than 0. Can you reject the null hypothesis at the 0.01 level of significance? Okay. First thing I need to do is I need to calculate my differences, right? So my differences are found by taking basically each value from 1 and subtracting the corresponding value from 2, right? So it's 1. Yeah, so it's like 15 minus 20, 20 minus, yeah, so let's see, here we go. Yeah, 20 minus 15, right? 21 minus 20, 24 minus 17, and so on, right? So let me come over to my whiteboard. I'm gonna need room here. So this is 20. So my D values are found by taking each value from sample 1 and subtracting the corresponding value from sample 2. If I did that, I would get 5, 1, 7, -2, and 0. The null hypothesis is given as mu d equals 0. Alternate hypothesis is given as the assumption that mu d is greater than 0. Alpha is given as 0.05. And just a reminder that mu d is defined as mu1 minus mu2, the difference between the population means. Okay. For the test statistic, that will be d bar minus mu d over s over the square root of n. D bar is found by adding up the 5 numbers in the D column and dividing by 5, right? So if you add those up, they add up to 11. You divide by 5, you get 2.2. S, which I'll actually call SD, that's the sample standard deviation. And easiest way is to take these 5 numbers, plug them into the list editor on your calculator and run the 1-var stats command. That would give you the SD value of 3.701. So then this, the T value is equal to 2.2. For mu D, I'll plug in 0 because I assume the null hypothesis is true. And I divide that by 3.701 over square root of 5. And I get 1.33. Then I'll go to my T chart. And because the sample size is 5, the degrees of freedom is 4. I'll go to my t-chart and I find 4 degrees of freedom. In that row, I find the 2 values on either side of 1.33. And then I will look at the corresponding area and right tail values, and that will tell me that my p-value falls somewhere between 0.1 and 0.25. Okay. And clearly my p-value then is greater than alpha, right? Because alpha is given in the problem as 0.05. So do not reject the null hypothesis. For the calculator, you would want to use t-test again. But for you'd use t-test, but you would just type these d values into your list editor. And then you would choose data as the input option and run that command. Okay, any questions? All right. So you have between now and Friday at midnight to take the final. It's available now. You can take it today if you want to, or you can wait a few days. It's your choice, but there won't be any extensions on that. So feel free to reach out by email anytime if you have any more questions. There is not any more homework due this week, so it's just the final exam. So I'm going to stop here unless there's any questions.